Hello, and welcome to the Reactor Room, where we solve professional engineering problems within the chemical discipline. My name is Zachary Brownstein, and in this video, we will solve the following problem. Kinetic data for the reaction of dinitrogen pentoxide with nitric oxide to produce nitrogen dioxide has been collected in the following table. The Arrhenius factor is most nearly... Okay, what I initially notice is that we are given kinetic data, and we are asked to find the Arrhenius factor. This is a hint for us to use the Arrhenius equation. So let's do that. We have K, the reaction rate coefficient, is equal to the Arrhenius factor times E raised to the negative of the activation energy over the universal gas constant times the temperature. Notice that all of these are a constant except for K and T, so any change in the temperature will produce a change in the reaction rate coefficient. We need to find A, but we don't know what the activation energy is. We can go about this both graphically and algebraically. However, when doing these problems, we may not have enough time, or we may not trust our freehand graphing abilities. So I suggest we do this algebraically. We're given a chart with multiple data points for K and T, so we can have multiple expressions. So let's start there. We'll have K1, and we're going to put in our equation. And we'll have a corresponding T1. And let's do the same thing. We'll make K2. And we're going to have the same equation, but we're going to have T2. What we can do now is divide them. And the A's will cancel, and we'll have the top exponent minus the bottom exponent. So let's write that out. We'll have K1 divided by K2. This will be E raised to, I'm going to take out the activation energy over R and distribute the negative sign, and that's going to produce 1 over T2 minus 1 over T1. Excellent. We now only have E as an unknown. What we could do is take the natural log of both sides and solve for the activation energy. So let's do that. We will have E is equal to, we'll have R multiplied by the natural logarithm of K1 over K2. And that will be divided by 1 over T2 minus 1 over T1. Okay, there's a few things to note. That is, first one, the Arrhenius factor are problems that ask that we have an expression that uses inverse molarity times inverse seconds. Molarity is moles per liter, so we need to have a corresponding unit for the universal gas constant. To make it easy, let's use a value of 8.314 joules per mole Kelvin. And knowing that, we also have to look at the K values and the T values. Notice that we have 1 over T in our expression, and we can't have 1 over 0. That gives us a hint that we need to actually convert our units from Celsius to Kelvin. We're going to add all of these. We're going to add 273 to all of these. Additionally, our K values, if you'll notice, they are all multiplied by 10 to the 3 or 1,000. So when we put this into our calculator, we'll need to divide by 1,000. We have 3 data points, but our expression just needs 2, so you can pick any 2. I'm going to choose the first one and the third one. So let's put that in. We're going to have 8.314. Let's put our units. And as long as we're consistent, it doesn't matter what K1 and K2 are. And I'm dividing by 1,000. And now we need to have corresponding values for the temperature. I'll put Kelvin. Oops. Okay. Notice that Kelvin will cancel out, and we will get a value of 65,472, and we'll be left with joules per mole. Okay, now that we have the activation energy, we can go back to our original expression and solve for the Arrhenius factor. We're going to move the exponent over. That will get rid of the negative sign. And we're going to have... I'm going to use the third data point. So we'll have 0.626, and our units are going to be inverse molarity, inverse seconds. We're going to have e raised to, all these units are going to cancel, so I'm not going to write them out. And let's see, our temperature is going to be 323 Kelvin. This will produce a value when we put in our calculator of 2.43 times 10 to the 9 inverse molarity, inverse seconds. Excellent. Okay, let's see what that's similar to. That looks similar to this value. However, notice that this is very similar to B, except this is changed by a factor of 1,000. I think you can get B if you forget to change these by 1,000. But I'm going to put in C, and we are correct. Thank you, and good luck.